Hello, everybody. I have to say that it's been a while since I've been presenting in Europe, and you all take your hangovers much more seriously than we do in America. This is kind of new content, and it's actually really not an advanced topic at all, but trying to take the concept of abstractions in software and apply them to modern architectures. So I found some pretty interesting parallels that I'd like to share with you and hopefully leave you with something to think about. So first off, I founded a couple of companies. I'm highly involved with the ACM. I've written far too much open source code that has ruined people's lives, and I farm in my spare time. But I'm here to talk to you about abstraction. So everybody who is a software engineer touches abstraction on a daily basis. A lot of us hate abstraction. A lot of us both hate and love abstraction as its true necessity in software. But it's really interesting that a lot of times we see abstractions as software hardware or software, but not often component to component in systems. So if you look at like a classic software abstraction, this is kind of what we're taught at university. When you talk about computer science, we take various classes depending on what type of thing that you studied. I actually studied to be an electrical engineer. And so you start with transistors, you do hardware function, you do microarchitecture, and everything else is not really a computer problem, right? So it's just like software people doing stuff that's not important on top of your silicon. What's interesting is that I actually really liked to code, so I didn't end up getting an electrical engineering degree. I ended up pursuing studies in distributed systems. So I'm a distributed systems person, so that really sits kind of on the algorithms, data structures aside from applications. So kind of get a different perspective looking down, writing code in higher level languages, and higher level languages for me is C. You know, that produces assembly language, and it's not often that you have to go into that assembly language to understand what's going on. High performance systems, you wind up down there quite often. It's very rare that you go down from assembly language into machine code, and it's even more rare that you would step one further down into instruction set architecture. But this is the type of abstraction that we know as software engineers, mainly because we don't want to deal with that other person's shit. Right? Like if you're writing in JavaScript, you don't want to have to deal with the V8 compiler, the V8 just-in-time compiler or the V8 system. Like you don't want to know C++. Like that's not it's not going to help you do your job right now. You have to go implement something. It's in JavaScript, and the last thing you want to think about is how that's implemented under the hood in C++. Helps to know how it works when it breaks, and you can go fix it. But in order to like keep your mind in one spot and become productive, you require that abstraction, right? And people who are writing C++, who think that they know all about how computers work, very rarely think about malfunctions in compilers that produce weird assembly or bad machine code. Mainly because they need to keep their mental context thin enough so that they can remain productive. This is like our classic concept of abstraction. So, one of the problems that I found in this is that is really only one dimension on which we abstract code. There's a lot of abstraction in code that is around skill set, which is what we just talked about, but there's also stuff around security and compliance. There are reasons to put code into different isolated buckets or create abstraction layers or interfaces between code in order to preserve security and compliance, regulatory compliance. If you have credit cards, for example, you don't just put them alongside your user-generated content in a database. That would be a bad idea. You separate those things and you build an abstraction layer to isolate them, not because you don't want to mentally think about those things, but you need to keep them separate for safety reasons. There's another way to isolate things is because they have incredibly different resource requirements. You have some task that requires incredibly intense disk usage but doesn't use much processor or RAM. You have another one like video transcoding, which is highly GPU oriented or CPU oriented. And you end up isolating those two things separately so that you can scale one up aside from the other one, and you put a boundary between those two things. And that boundary is almost indistinguishable from a software abstraction, because when you're outside of that service, you don't have to think about how it works. Safety and correctness is an interesting one. This is common in distributed systems, where you isolate certain things like raft protocols, multi-paxos, things like that, consensus algorithms. And the reason that you do those is because it is a world of pain when you fuck that up. Right? So you isolate it away from a developer, and you don't allow them to break through that abstraction layer, because the risks of correctness violation is severe. Like lots of data loss, the whole system falls apart, it doesn't work, things don't converge, bad things happen. So you end up isolating those behind an abstraction layer that just says, store this key value pair, please. And it says, okay, I did it. And behind that, behind the scenes, it implements all of the distributed systems algorithms. And another one that's really interesting, which I focus a lot on for resilient systems design, is availability. And this is a common one, and this is probably the only reason that I truly love microservices, because so I studied distributed systems at university for way too long. So 7 years before I was asked to leave. The interesting part is that I kind of swore that, like, I'm not going to do distributed systems because this is horrible. So then I go get a job and I help people scale things up, and created microservices, and now it's like, shit, I'm right back where I started. Everything is broken for the same reasons I studied. So all of that knowledge is now applicable. The interesting part of that is that when we had these big monoliths in our systems, we had this huge problem where if we needed 99.99% availability or reliability, we had to do that for the monolith. And it turns out that that's really, really hard. But if you take certain components of your system and you say, oh, you know what, like search for the web page, that one only needs to be up 99.5% of the time. Transactional billing needs to be up 99.9% of the time. Inventory and recall only needs to be up 99% of the time, and because if it's delayed, I can still ship the product out later. You start to isolate those things, you can start making different design decisions around the availability of those components. So that's, to me, the heroic part of microservices. It's around availability, and it's around security, compliance, regulatory compliance, being able to take like problems that really suck and put them in a box. Put an API around it, give it to a team, and allow them to solve a much smaller, more refined problem set with better tooling for that problem set, and not have to carry the baggage around of like rendering crap in the web. Right? So there's all sorts of complexities in the systems that we build. We don't want it all in one spot. So this is the problem with abstraction, is that it's not just on that like software to software, software to hardware level. It's around all of these different dimensions, and most of the problems that we have, turns out that things need to be available or not. There's probably safety or correctness concerns in your system. They do use resources, it turns out. People write the code, so there's skills questions. So all of these things are always a concern in all of the projects. And when you choose to write an abstraction layer, you're really choosing one of these dimensions. And it's a lot of times, as software developers, we only ever think of this picture when we think of software abstraction, so we tend to do it this way, which is very dangerous. Microservices have kind of brought us forward a little bit in thinking about that differently. But just as an example of an architecture, this is an incredibly simplified version of the time series database that we write at Socrates. This is all sorts of different abstractions sitting on tops of other things, but it turns out there's a lot of different data formats and write patterns and read patterns that come out of it. So all sorts of things happen here, and we have this beautiful little elegant layer in the front that's the time series database, and you say, hey, I have some data for you, and it goes, great. And then you say, hey, I need some data back, and it goes, here it is. And so it sounds beautiful, but it turns out that there are other APIs, and they can't run fast enough against that. So in high performance world, you end up having these intentional, you either have abstractions that leak their implementation details, or you have abstraction violations on purpose to achieve these. So we have two serious things in there that would never run correctly if we were to use the top-level APIs in that system. We have to kind of just reach up under there and do things in the database that are pretty atrocious in order to achieve those performance gains. So those abstractions, because they're multidimensional, not only because they're multidimensional, but necessarily because they're multidimensional, will never align in such a way that you don't have to cross those boundaries. It's very, very rare. So the second problem with abstractions is that people tend to aim at elegant code. You refactor and you build these beautiful things where you've written this system and you're like, oh, well, I can generalize this. This is great. All right? Stop doing this. Like, there should be a reason, there should be a call to action to generalize things into abstracted APIs. And there are reasons that kind of drive how you do this, how you approach the problem. And if you don't have the information, you always do it wrong. So there are constraints around performance and scale that typically you know as an engineer when you're starting to build on your product. You say, well, how is this going to be used? And someone says, oh, we're going to be bigger than Google, so we're going to scale to here, and it needs to be really fast, so we're going to scale to here. And you're like, okay, well, that's great. But the thing that you don't know is you don't know who's going to be using your API yet. Right now, it's actually just you. And I will say the cardinal sin. How many people here have developed a general service thing with absolutely no consumers at all, not even yourself? Uh-huh. All right. So guarantee you got that API not quite right, right? You learn so much from a consumer of that thing. So the fewer consumers you have for a specific set of generic, potentially generic code, the less likely you are to nail the API in a really consistent and useful way. So you should always delay. So one of the rules that we have internally, I think I learned it from something I read from some Sun engineer at one point, was that it's a cardinal sin to produce an abstraction or an API without a consumer. And a test is not a consumer, right? Like an actual user in anger of this API needs to exist alongside the API in that first commit when it goes into a repository. At least one. So you don't build a system for potential users. It's not Field of Dreams here. If you build it, they will come and be very, very angry. So this is a problem that we constantly face. And this one's actually really easy to solve by simply delaying. You write some code and you go, I'm going to reuse that. I should generalize it. It's like, no, you should copy and paste it, and you should reuse it again. And then when you hit that third time, maybe the fourth time, then you can figure out all of the lessons learned and all of the copy, paste, and edits that you did to understand exactly how that generalized service starts to get used under the hood, so that you can understand how to build that abstraction layer in a good way. So these are these kind of general problems. The last problem is everything you build is crap. Everything I build is crap. I've been a software engineer for a long time. As an engineer, very differently from an academic, like an academic can write a proof and it can be proven correct. In computing, you can do some formalized proofs and things like that. Those tend to be a little bit more academic. But as an engineer, if you don't look at what you wrote 5 years ago and have some regret, you're not introspective enough. Like, that is fundamental to improving your craft. Like, you should be self-critical of what you've built. You can absolutely be proud of what you've built, but you should be self-critical because what you build doesn't tend to work, right? I'm amazed that the internet works at all every day. I mean, I've seen everything down to, basically firmware and software on, router cards and things like that. And you're like, I don't know how the packets get there because this is shit. So everything is stacked on turtles, and it's amazing that it works. And what that means is that when things break, you have to fix them. You have to go in, you have to understand the failure, right? And I love that. That's what keeps me going to work every day, is this pathology of failure and understanding why this thing suddenly exploded after working for 7 years. You will have abstractions in what you look at, and when you work up and down in an abstraction stack, it's an incredibly inexpensive operation for analysis. If you're looking in your JavaScript code for a bug, and it is not a V8 bug, it's a lot easier to solve than if it's a V8 bug. If you're looking at your C++ code, well, it's never actually easy to solve because we've all seen C++ error messages. But if you're looking at C code and there's actually a problem with your C code and it's not a compiler bug, it's significantly cheaper to analyze, solve, and remediate that problem than if it's a Intel firmware issue from the exact code sequence that was produced by that compiler, right? That would be like 2 layers of abstraction lower. It's a pain in the ass to solve that. So when you build abstraction layers, the super senior engineer with a lot of experience has sort of a spidey sense about the types of failures they expect to see and how often they will transit those layers, those API abstraction barriers, and they'll optimize for that. So the idea is, and kind of the whole premise of the talk, which I have little time left, so I'll keep going, but is that when you design these layers, you need to optimize where you put the boundaries of your software so that you minimize the cost of transit between layers. So I like to think of abstractions, it's like technical debt. I really like financial metaphors. So abstractions are kind of like loans. You're borrowing something, right? What do you owe? You owe performance that you can no longer get. You owe the constraints of the boundaries of those systems. But the interest that you pay on that loan is the number of times you have to analyze that across its boundaries. So in real life, a couple of really quick examples, which I'm not going to dive into. You're more than welcome to strike up hour-long conversations about this afterwards with me. So we built a time series database. It's super fast, it's super scalable, and it turns out that writing data to disk and getting it off is not as easy as you'd think, and that when people try to write mathematical code inside of C, they segfault, almost always, because the people who know math and the people who know C tend to not be the same people. So we had this problem that we have this event-driven, multi-threaded system called libmtev. It's open source. There's a link on the last slide. That we build all of our internal applications, including our database, on top of. And we needed to have this accessible to engineers, software engineers that were really data scientists more than software engineers, and we wanted them to be able to rapidly prototype code. We needed it to be fast, and we needed it to be safe so that you don't segfault your database. Turns out that even taking a few minutes to come back online is potentially disruptive. So what did LuaJIT give us? So Lua is an embedded language. It embeds in C or C++ or Rust, and it's a higher level language. It looks, nobody shoot me, it looks a little bit like JavaScript, except it doesn't suck. So the beauty is that Lua is really elegant. It's a functional language. It's really elegant. LuaJIT's really fast. But the reason that we chose LuaJIT was because it's cheap to make abstraction violations. The Lua boundary, the C boundary, we're constantly fighting for performance there. And sometimes we need to do things that probably are a little bit unsavory and go into C and just put things on the heap, a lot of unsafe operations and all that kind of stuff. And Lua particularly makes it inexpensive to do that. So we knew that when we embedded, because we looked at embedding Python, we looked at embedding Julia, we looked at embedding R, and all of those things were great languages for data science, but we realized that every time we would have a problem, we were going to have some big engineering effort in the performance realm to fix it, whereas LuaJIT was like optimized to make violating that layer cheap. So we could be bad and not pay for it all the time. So it's really a pretty interesting choice there. Another one is database abstractions. Everything seems like you should abstract it with a database. I'm writing a key value store, so I'm just going to have a key and a value, and I'll put it in, and I don't really care about the implementation so much. So we reasonably couldn't decide what implementation we wanted in the beginning. We've been through like 4 or 5 different embedded database implementations, and it turns out that every single time we screwed ourselves by abstracting it. This one was a really hard thing to remember. So it turns out that databases basically update, or they append, or they delete data, usually all 3. They tend to read data randomly, sequentially, and bulk, and when you do all of those things, they're not good at very much any of them. So you really have to focus in a database. For a time series database, appending data is the thing that you can never be bad at. And then reading randomly, If you're going to be drawing graphs on the screens for people, you have to be able to be really good at that. It's hard to end up combining random reads and really large bulk sequential reads in an optimized way in a database. So what happens there is that you kind of know that when you get down to it and you have to build, for example, rebuild a node. In order to rebuild a node in a distributed system, you have to ask all the peers for all their data. That's not random. That's like a big full table scan on all the other boxes. You're going to have a layering violation there. And you got to own it. Like, that's just going to happen because the alternative is really crappy. So it's really interesting that we made a lot of mistakes in the way that we abstracted that. Because I think we thought we could do it elegantly. And we didn't optimize for the fact that there was an imminent layering violation that was going to happen. And the last one, which I think is sort of the most interesting one, is there's all of the work for this one is open source, is this idea of concurrency limiting and fair scheduling. So a database, just as like every other systems, they have a lot of tasks that they do that consume resources, as you'd imagine. So in any app, when you ask it to go do something, say I want to go read 10,000 time series and calculate some sort of mathematical transformation across them and then cluster them and find outliers. So what would that require doing? Well, it would require doing 10,000 pseudo-random disk reads. Well, I can't just do 10,000 reads at one time. I can only do so many. So the universal scalability law, which is a really interesting and simple thing to understand, to sum it up is concurrency always makes things faster until it does not at all, right? So if you have, say, 10 web servers, and each one can do 1,000 requests a second, you can get faster and faster until up to about 10,000 requests per second. Then you go to 12,000, and it turns out that they're not going to slow down linearly. You're going to thrash, right? So you have to be able to limit the concurrency in these systems so that you don't kind of thrash them to death. And what we ended up building here was an abstraction that allowed developers to kind of generalize concurrency management around resource workloads. So you can create event pools and say, this one is going to be about random like time slice reads. And depending on the system, I'm going to allow it to go up to like 30 concurrent operations. And then when people are in the system and they need to do one of those, that work gets scheduled into that dynamic pool, and those resources get kind of dynamically controlled and expanded. And that was one of the abstractions that took around 6 years to arrive upon because we kept doing it different ways, right? This was a case of, if we had done this in the beginning, it would never have worked right. But we had lots of consumers over about 5 or 6 years of development, and when we kind of stepped back and looked at the whole system, we said, hey, there's a pattern in here that is reusable and useful. And then at that point, we were able to build, of course, still a broken API, but an API that was really, really useful for current workloads and future workloads. So what are the lessons here? So what lessons you should walk away on is there is no shame in abstractions, okay? They are absolutely and fundamentally required. You can't get your job done without abstractions. Can you imagine having to think about like transistor state changes every time you like load a web page? That would be crazy. So abstractions are here. They're here for a reason. That's not a bad thing. The thing that we really need to do carefully when we're building things is to choose the dimension on which we abstract very, very carefully to minimize future costs. Right, so think of the leaky abstractions or intentional violations of boundaries of abstractions. Think of those as interest payments on the loans. The interest payment or the interest rate is relative to how accurately you choose that dimension. So for example, if you are storing credit card information and you choose to abstract it via an API and not isolate it into a service, the cost that you pay in security audits and potential liability is enormous over time, right? Because you're going to have the potential for inadvertent layer violations there. So choosing these is really important. They can be around code complexity, security, compliance, availability, ownership, and you should think about those things. Sometimes you can abstract around more than one boundary. Lesson 3 is to maximize the number of stakeholders you have before you make decisions. Because if you had this beautiful thing that would be useful to everybody and you have 0 consumers, the first time you build it will be the only one that's never used. Because when you have a first user come up, they're going to say, this API blows. This is horrible. I can't use this. And then they're going to come back and you're going to revise it and you're going to build something. Oh, it's great. It's better now that I have a stakeholder. And then you're going to get a second stakeholder and they're going to be like, this is built for only their problem, not my problem. So the more stakeholders that you can build on your solution before you generalize and abstract will make you build a much better, more future-proof API and abstraction boundary. Whether you're a fan of test-driven design or not, tests are not consumers of APIs. They are testers of that you built what you intended, not that what you built was any good, right? So tests do not count, and other programs' tests of your API don't count. It's actual users delivering value on the API that count as stakeholders. Lesson 4 is that leaky abstraction happen. Okay, this should never be the goal. You shouldn't set out to say, I want my abstraction to leak implementation details. But there are a lot of times where you want to build an abstraction around something to provide developer convenience, right? You don't want to have the developer thinking about all of the details of the implementation all the time. But because you're in a high-performance system, you know that they're going to be violating that boundary and need insight to the implementation details. So instead of trying to hide it and have them breaking through, you should just unapologetically leak the abstraction, right? That's not, and it's not a cardinal sin, especially in high-performance systems. So the most common, in my experience, and it's probably biased from where I work, but the most common reason for violating abstraction boundaries is performance. You have something that is fucking slow for no reason, and you look at it, and it's because there's just an API that, you know, does iteration over keys out of order because that was the API that was there. And then you look underneath the hood, and you're like, I can do this in 1/1000th of the amount of CPU cycles or resource usage, and you really should do it that way. A lot of times, if you had leaked the abstraction, if you had leaked the implementation through the abstraction a little bit more, one, the developer wouldn't have made that mistake in the first place because it would have been more obvious that they were really screwing it up. And the other is that they probably would have requested an API addition or been able to kind of manipulate the implementation in unsavory ways to accomplish their goal. So, and yes, of course, that produces a tie to the implementation that's a little more hard to sever, but in high-performance systems, this is what happens. And I think that I think this is the last lesson, and I would say it's probably the most important thing is that in life, like, there aren't perfect decisions, right? And decisions simply have costs. The reason we make decisions is to get return, right? This is a simple return on investment question. So abstractions and violations of those abstractions happen, and they should happen every time you gain more than you spend, right? So when you violate an abstraction layer, you make it harder to upgrade the code, you make debugging it a little trickier. But if you gain more than those potential costs, it shouldn't be a question, it shouldn't be embarrassing, and you should unapologetically own that. So you assess how much it costs, you assess the burden that you will have for doing the violation, and then you accept it and you move on with life, because you need to solve the next problem. And that's it. So you have questions? Percentage-wise, how many businesses in the world? That's a fantastic question. I hope everyone can read that on the screen. My guess is that probably not that many. Microservices are a trend. I think microservices in concept, the model of them, how many people here use a third-party service for something, right? You interact with an API that you don't own. Okay, that's just somebody else's microservice. So in a lot of ways, as soon as you're talking over the network with a controlled protocol, you are relying on a third-party system. And there are advantages, and that's exactly why you're doing it. But I think that the kind of the craze or the trend on microservicing the crap out of everything that you have, that pendulum will swing back. So there are ways to accomplish independent teamwork with high velocity without using microservice models. So I would say that the best thing about microservice models is the way that they encourage teams to autonomously develop code and the way that they have to communicate with each other to establish protocols and APIs. Those build strong contracts between services that you can skip out on when you're in a monolith. But you can do those in a monolith. So I think that if you can gain all of those development benefits and the development practices from microservices, but not have to deal with all those tragic distributed systems problems, you kind of win a little bit more. So I would say that I can't even swag the percentage, but it's certainly less than 50% that would benefit. You mentioned you shouldn't build a system before there's a consumer for it. API first approach is horrible. And I will also, because I like to offend people, test first is horrible, right? That makes the test your first consumer. It's the one person who doesn't pay you anything, right? They don't pay you any money, right? Like customers, that's your thing, right? You have to have a customer for your product before you build it. Going to build it and then trying to find a customer for it is like literally academic. You're creating a problem to find a solution. You're creating the problem to find a solution for it, right? People have actual problems. So I think API first approach is pretty poor. And it's not that you shouldn't build systems. I mean, you absolutely build systems before you would build systems as a part of something that's delivering to a customer, but the idea of componentizing them and providing API surfaces on them is something that should be done after they've been consumed multiple times. You'll learn a lot. I think to couch that, when you know that there are going to be a lot of consumers and you've been doing it for many years and you're a senior engineer, you can sort of intuit and sort of guide yourself into an API will not be hard when we do it sort of approach to things. So you can accommodate API first without actually leading with the API. What do you think about teams dedicated to write common libraries? None of our computers would work without those. Like, how many people here use libc, right? If your system boots, you're using libc, so yay. So I think that the common libraries thing, I think that when you start to do that in organizations, like in organizations that have tools development teams and things like that, it's a little easier to have lack of alignment. But fundamentally, I don't think that's a problem. But if you are building a component as an isolated group, you really need to treat it as a product with customers and stakeholders. So that's a very important shift. A lot of people who write libraries and build their APIs and maintain them, treat them like their children. Don't do that. They treat them like their hobbies. It is a product, and it turns out you can lose your market share. As soon as you start not accommodating users and not being convenient and not being friendly, even to the people that are 3 cubicles down or 3 offices down, they will find a new way. Developers are not loyal, and they are all about convenience. So if you don't treat the things that you build as products, even internally, you will find yourself out of customers. So next question. If there are 10 components in a complex system and each one has 99, I can't do math on the stage. The whole system's reliability is down to 99.9. Does this complexity kill reliability? So, that's it's an interesting question. So people tend to think that a system is either on or off, and that is never the case. So when you have different components that have different reliability requirements, it only has this effect of being a multiplicative probability problem when all components rely on all other components, which if it's the case, they should not be separate components. Like if they all literally rely on if every component in your system literally relies on every other component in your system for everything that they do, that is literally one component. Like, you've decided to make the problem very complicated by pulling them apart. Congratulations. But you really don't want that. So the idea of separating them is that if you pull, for example, credit card processing out of your system, it doesn't affect search, right? Like, I don't know, unless you charge people to search, but you know, by isolating the components, you really only have those probability multiplications across components that are directly dependent on the service that you're providing. So it doesn't end up being that bad, is the answer. The beauty of that is that even none of them, they will all not be 99.99. The one that's 95% reliable, the reason that it's allowed to be 95% reliable is that none of the service paths that it is in the chain of have high levels of availability requirement. That's why that happens, and then it turns out that building a 95% available service is really easy. So then you can focus on harder problems. How do you assure that when you violate abstractions, you don't go into other extremes? I wish I knew the answer to that. I've been down the rabbit hole in dark places. I would say that as soon as that you have development of a product that is impeded by people's lack of knowledge due to implementation leak, right? So you have a person who comes in, for example, if you were to leak the abstraction between C++ V8 and JavaScript to the point where you couldn't really code JavaScript very well for most problems without knowing C++, you would notice productivity nosedive on your entire JavaScript development team, right? And that would be that would clearly evidence that you've violated an abstraction boundary in a way that has cost burden that's too high. At the end of the day, you know, but it's extreme because it costs too much. But ideally, you don't. So I'm not a huge fan of leaky abstractions. I'm much more a fan of intentional violation of abstractions. Which is that you expose a private API, and if you use it, that's on you, but you don't need to use the private API to accomplish the goals of the product. So as opposed to a leaky implementation where, like, there are certain APIs that you can't change the underlying implementation basically you're stuck on the implementation because you've exposed an API publicly that's commonly used that's like idiosyncratic. At what point should a team consider to break down a microservice which starts to grow bigger and bigger into smaller ones? To me, I think it really depends on business goals. That's a really hard question. At some point, you have a set of objectives, and if you're meeting all your objectives, then you don't have to do anything. And if you're not meeting your objectives there, they're probably around code quality, or they're around time to market, or things like that. And depending on what those improvements that could be had are, I think that would sort of dictate when you would shift into microservices. I would say that if you're running, to me, the two primary reasons that I think that you tend to almost always get positive gains on microservice breakup are for regulatory compliance requirements, because making your entire tech stack regulatory compliant will put you out of business. There is no way to do that. I mean, even banking applications have components that don't, they have isolated components that don't have to do that. And the other one is availability. So if you have certain systems that you know, like some systems, it's just easy to stick a row in Postgres and get it back out again. And I tell you what, if you need a 99.999% reliable system, it's probably not the path you want to take. But if you can isolate the things in your system that need less availability and allow them to use a more simple, more intuitive development path, then you get higher team productivity and all of that stuff. So that's, I think, again, it comes down to what you're trying to solve for. What new IronDB brings to the table? Are there not a gazillion? There are not a gazillion other time series databases. There are, I would say that there are about 4 or 5 that do telemetry data, and there are probably about 8 to 10 that do event data. We're a telemetry data database. to not go into a product pitch, but operability, large scale. We do histogram data, and we embed analytics engine inside the database. Those are big differences. If you're really interested in that, you should come talk to me afterwards so that I don't bore anyone else with that. And that's it. Thank you.